Welcome to this lecture on sequences and summations. We'll start with sequences in this first segment. Now, a sequence is a special kind of function. I will let you review that hierarchy of concepts that goes all the way from sequence to function to relation up to set. Remember that a function is a set of pairings. So it's a set of pairs where the first element comes from a set called the domain, and the second element comes from a set called the codomain. While a sequence is also a function, but it's a special kind of function because the domain is forced to be a set of consecutive integers. Typically, the domain of a sequence will be the set of natural numbers from 0, 1, 2, and up, or the set of positive integers, those that start from 1 up. So a sequence is a special kind of function. The only constraint is that the domain be a set of consecutive integers. It could be an arbitrary set of consecutive integers. It could even be a finite set. But in general, we'll take these infinite sets as the domain. So if a sequence is a function, then we know what the domain is. It's a set of consecutive integers. What are the elements of the codomain? Well, it can be anything, but each of these elements of the codomain is called a term. So if the sequence is called A, then each term is called A sub n, where n again is the element of the domain to which that term corresponds. So A sub n is also called the image of the integer if you look at the sequence as a function. So a sequence is a series of terms, A sub n, and the whole sequence is sometimes written like this. The name of the generic term in braces. Now don't be confused, this is not a set, it's just a symbol to represent the whole sequence. Now, to make this more concrete, let's look at a few examples of sequences. So the first sequence is the sequence A sub n, where A sub n is defined as 1 over n. And notice here it tells you the domain is the set of positive integers, since we don't include 0. So what does that mean? Now every time you want to know the nth term of the sequence, you just plug in the value of n in this formula here. So A sub 1 is equal to 1 over 1, which is equal to 1. A sub 2 is 1/2. A sub 3 is 1/3. You see it's a sequence of elements that gets smaller and smaller every time. In general, A sub n is 1 over n. So n goes arbitrarily large, so it's an infinite domain, namely is this one. So these are the terms, A sub 1, A sub 2, A sub 3. This is the generic way of representing the sequence, the whole sequence, which is not a set. So, in case you don't see it quite yet, why is a sequence a special function? Well, it's written right here. This is, look at A as f of, so this is f of 1 is 1, f of 2 is 1/2, f of 3 is 1/3. See, the domain is a set of consecutive integers starting usually at 0 or 1. So, that's just a made-up sequence, specific one. Let's look at a second example. This time, it's not just one sequence, but a whole family of sequences called geometric progressions. So, a sequence is a geometric progression if the terms in the sequence are first a constant a, and then a times r, when r is another real number, and the next term is a times r squared, and the next one is a times r power 3, and so on and so forth. You could see the pattern. So a geometric progression is defined by two terms. First, the initial term, which is a, the constant a, and then a real number r called the common ratio. So why is it called the common ratio? Because if you take any term and you divide it by the previous one, you always get the constant r. Notice ar divided by a is r, ar squared divided by r is ar. In fact, another way to look at it is to go from one term to the next, you just multiply by r. If that is how your sequence is defined, then your sequence is called a geometric progression. Now, let me make an observation about two different ways of defining a sequence. One way is called a closed form formula. So, for example, here is a closed form formula for defining a geometric progression. It says A sub n for any n greater than or equal to 0 is equal to a times r power n. Now a is the initial term, it's any real number, and r is the common ratio, it's also any real number. Notice this formula is enough to define the whole sequence. That's why it's called the closed form formula, because to obtain any term in the sequence, all you have to do is replace n by an arbitrary integer here, and you will get the value of the term right away. You just plug it in. So this is a closed form formula for a whole geometric sequence. Now there's another way you could define that geometric progression, and you could use a definition like this one. You say a sub 0 equals a, and then a sub n is r times a sub n minus 1, which is the previous term as we argued before. And this is true for any n greater than 0. So notice this kind of definition has two parts that go together. First you define the value of the first term, and then you define the value of any other term as a function of the previous one, namely r times the previous one. This kind of formulation is called a recurrence relation. Now we'll talk more about this later in the course. These are very important for computer science and to analyze the runtime of algorithms. But for now, a recurrence relation, think of it as a recursive definition where a sub n is defined in terms of a smaller version of itself, namely the previous term in the sequence. So together, those two equalities define a recurrence relation, or if you will, this is the base case and this is the recursive case. So make sure you convince yourself that those two definitions are equivalent, and there are two different ways of defining the same geometric progression. Now let's go back to our first example and ask ourselves whether this definition was a closed form formula or a recurrence relation. Well, clearly the value of a sub n is defined directly in terms of n, not in terms of the previous element a sub n minus 1. So this is a closed form formula for the first sequence. Notice all you need here is the value of n. If you plug in 1,000,000 for n, you will get a sub 1,000,000 in one step. You don't need to compute the previous element and the previous element of that one before that and so on. So let's try to come up with a recurrence relation formulation for this same sequence. Notice we must first define the first element or the base case. Now in this case, 0 was the first index, but in the first example, n must be greater than 0 because you can't divide by 0. So the first element is going to be a sub 1, and of course it's equal to 1, 1 over 1. Now, how do we compute a sub n as a function of a sub n minus 1? In other words, how do you go from 1 over n minus 1 to the next term, which is 1 over n? Well, you just have to multiply a sub n minus 1 by n minus 1 over n. So this is a recurrence relation formulation for the same sequence. Now, is this sequence a geometric progression? Well, it's almost a geometric progression because to go from a sub n minus 1 to the next term, a sub n, you just have to multiply by a number. Unfortunately, that number is not a constant. It's not a common ratio between one element and the previous one. That's the same for every pairs. That's the definition here of a geometric progression. So this number is not a constant since it depends on n. Therefore, this is not a geometric progression. Now, let's look at a third example or family of sequences called an arithmetic progression. It looks like this. The first term is a constant a. The next term is a plus d, where d is another constant. And then the third term is a plus 2d, a plus 3d, and so on and so forth. So in an arithmetic progression, the initial term is a constant a, and the characteristic here is that there's a common difference between two consecutive terms. In other words, if you subtract any term from the next one, you get the constant d. In other words, you're adding d to go from here to here, you're adding d again to go from here to here. So the difference between a geometric progression and an arithmetic progression is that in this case you have to multiply by a constant to go from one term to the next, whereas here you have to add a constant to go from one term to the next. So what I want you to work on now on your own is to take any arithmetic progression like this one and to give a closed form formula for it. So it's a formula a sub n equals some function of n. And then as a second exercise, I want you to come up with a recurrence relation formulation for an arithmetic progression. Remember, for this one, you need two parts, the base case and a recursive case.